All right. So here I've been giving you some estimators that I just kind of made up, but in general there's always a very sensible way to come up with an algorithm to guess a number. If I tell you how that number is defined relative to the population, there's always a very sensible way that you can do to guess from a sample, and that is to do the same thing to the sample that you would have done to the population had you had it, in order to calculate the number you're interested in. So this is the general picture here. So we already saw this. For example, let's say that this your estimand of interest is the expected value of some column, right? The expectation, the definition of the expectation is just the average value over the entire population. And so what's a good estimator of that? If I have a sample, I'm just going to take the average, not over the entire population because I don't have it, but average over my sample. But it's the exact same process. I'm just averaging over sample instead of population. So that is the idea of a plug-in estimator. And it's called a plug-in because you can think of it as like, okay, you have this process, this algorithm, or a kind of like rule that if you give me the population, I can tell you how to compute the value of the estimand, right? So in the example I gave is, well, take the average of one of the columns. That gives you this. So whatever that rule is, I'm just plugging in the sample instead of the population data. I'm plugging that into that rule to get my estimate. So that's why it's called a plug-in estimator. So here, this is the example that I gave you. So sample averages are a sensible approximation to true or population averages. You can see that here on the left-hand side, I have the expected value of x. Let's say that's what I care about. That's my estimand. That's defined as the value that x takes for each person in the population averaged over however many people are in the population. And then over here, we have the value that x takes for each person in my sample. And so I could, sometimes you'll see this little hat over the E, and this just means sample average as opposed to population average. And all we're saying is, okay, well, these two averages should be kind of similar, okay? So thing on the left, estimand, psi. Thing on the right, the estimator, empirical estimator or plug-in estimator. Those are kind of interchangeable terms for the same thing, psi hat. So this is one way that you can build an estimator. There are others, okay? I'll talk about it in a second. But so in code, if you have... here I could also put like data. Oh, sorry. Instead of data, I would put population. Okay. So if this were in code, I'm showing you the same thing. Here, this is the population mean, and here this is the same thing. The key to understand is like I'm just using this exact same function. The only thing that's changing is whether I'm putting population or data into it, and that changes it from the estimand, which is fixed in reference to the population, to the estimator, which is going to be a random number that depends on what data I get. And here's a more complicated example, again showing it mathematically first in terms of a mathematical notation. This is the risk ratio that we talked about, where we have the expected value of y given that the exposure happened relative to the expected value given that it didn't happen. And then over here, we have the empirical estimator, which is nothing but the sample average value of, this should be a y. Sorry about that. So the sample average value of y in the group of people in the data that had the exposure relative to the sample average value of y in the group of people in the data that did not have the exposure. So same idea. And here it is in code. So if I had the population data set, all I would need to do to get this to go from the estimator to the estimand is I would have to scratch out data here and put population. And we already talked about what this code does. It just implements this mathematical idea. You can write it mathematically, you can write it in code, same thing. So not all estimators are plugins, though, okay? So for this risk ratio, this is a way that you can estimate it. But there are other ways that you can estimate it that don't depend on you just doing the same thing that you would do to the population data, right? So here's one of them. For this risk ratio, what you could do instead is you could run this this logistic regression model, and you could get this coefficient out, and you could exponentiate it. You could say, that's my guess. And we'll see more about this later in the course. I'm just showing you that this is what's going on here. What is this regression model is much more complicated than just taking some averages and dividing them, okay? So this is not what you would do if you had the population data set to get this number. So this is not a plug-in estimator. Of course, the question is it better than the plug-in estimator? Is it worse? Under what conditions is it better and worse? What do we mean by better and worse? Those are valid questions. But the point of this section is just to give you one method that you can use. If you see an estimand, you can immediately have an estimator that could guess it. Okay, so let's have a look at these. So let's say I have a sample of n xy measurements, and I'm interested in the following population quantities. How can I estimate them from the data I have? So I want to construct the plug-in estimators mathematically. So just like write out the formula that corresponds to the plug-in estimator, and also write R code for each of them, assuming that my data is in a data frame called data. So let's start with the first one. Sorry, I have 5 here, but there's only 4. So scratch that out. Okay, so let's do this first one here. So the estimand is the covariance of x and y, which is defined as there's 2 equivalent definitions, but I'll use the first one, just the expected value of x minus. I'll write here expected value of x, y minus expected value of y, expectation of that. So remember, this is kind of measuring if x is far away from its mean at the same time for people who y is also far away from its mean, then this number will be big and positive. Or if they're far in the same direction, if x is smaller than its mean when y is bigger, then this will be a negative number. So it kind of measures if x and y are moving in the same direction or in opposite directions in the population. Okay, so this is the population quantity, right? These are population averages. How do I turn this into a thing that I can guess from the data that I have? So the idea of the plug-in estimator, remember, is just replace the expectations with averages, sample averages, or do whatever you would do to the population, do it to the sample. So if in the population now would be average, these would be averages over everyone. In the sample, I'm just averaging over the data I have. So this outer expectation becomes a 1 over n, and I'm just averaging over the data. So little I from 1 to n. And for the observed values that I have, it's going to be xi minus, now I have an expectation of x. So in here, I need to compute what that expectation is. And then same thing for y. And I think that's it. So that is the what we call the sample covariance. And we can put that into R if we want. Okay. This is janky. Sorry, guys. Okay. So maybe that's as close as we're going to get. So let's make a little data set. I'm just making some random data. It doesn't really matter. I just want to have something that I can use. Okay, so now I have the data. You can see, great, 100 samples from this thing. So now let's do this thing to that data. So let's we could do it in steps. Maybe that's best. So let's first compute this inner expectation here. And we do the same thing for y. And then we can take the mean off of x. Just do it like this. And now I take the product of those. So I'll just show you what that looks like. Okay, so this is a column of 100 numbers. That represents this product, and then I need to average that. And this is my number. So this is my guess of the population sample covariance. In this case, it's the guess I get is near 0. The reason is because the actual joint distribution of x and y, they're independent, and so the covariance is, you can see my function that I is generating y has nothing to do with x, vice versa. So the population covariance is 0, but here you can see my guess from this 100 samples is some number that's slightly different. And indeed, if I generated a different sample, same distribution, different sample, I run it all again, I get a different number, right? Before I got like this minus 0.09, now I get 0.22. You can keep doing that. Different number every time. It depends on what the data that I get is, because this is some function of the data. And if we wanted to, we could even put it inside of a function to make that clear. So I could call it like sample covariance, some function of the data, and then I wrap this up, put it in a function. Okay, and now I can call and you see that I get that answer. I could, if I regenerate the data and run it again, different answer. Okay. This is very wordy. You could do this much more concisely if you wanted to. I think you could just do like mean of x minus mean x times y minus mean y. This does the same thing. I just wanted to show you how to kind of do it step by step, so that you understand that what we're calculating as we do this. Okay, so now I have my function. Okay, there we go. It does the same thing. Okay, I think that's all I wanted to say about the sample covariance. Oh, there's also turns out this is already built into R. Hopefully this does the same thing. Okay, slightly different. That's because this is calculating it's actually a slightly different estimator, because our covariance estimator is an actual plugin. So it's 1 over n. The one that R is using has an n minus 1 here, I believe, which we can verify. Well, probably see it somewhere. Well, here's a way to know for sure. Let's just multiply that, whatever R gives us, by, did we have n already? Yeah. Minus 1 divided by n. Okay, which is the number that we got, right? Yeah, there we go. So it's exactly that. So R's version is not this plugin estimator, okay? So it has this covariance function, which is an estimator of the population covariance, but it's not the plugin estimator. The plugin estimator has a 1 over n because it's just doing the average, but theirs has a 1 over n minus 1. What? Why? Well, that has to do with stuff that we'll see later. It turns out that using an n minus 1 makes their estimator unbiased, whereas the plugin is actually slightly biased. But the plugin is actually better in larger samples. And there's a question on the homework assignment, I think it's on the challenge assignment, about exactly this. So you'll see that. But this is actually kind of cool to see that the default estimator on R is not this plugin. Okay, cool. Let's do the next one. This expectation here. We've actually already seen how to do that, right? So we know that's the sample average of x, but just for those people where y is greater than 0. So mathematically, how would we write the plugin for that? You can kind of let's just fudge it at first, right? So let's say that's 1 over however many people have y greater than 0, okay? And then we're averaging over just those people where y is greater than 0, x, okay? So sum of values of x where y is greater than 0 divided by however many people where y is greater than 0 in our data set, okay? And if you want to make this a little, I mean, this would be understood. Like if you wrote this in a math paper, people would know what you're talking about. But if you want to make it a little more formal, you can do it like this. You can say, well, there's a couple different ways, but okay. So let's say this n. How many people is it that y is greater than 0 for? You could do it like this. I'm just going to add up a 1 if I see y is greater than 0. So this is the indicator function of where y is greater than 0. Every time that happens, so I'm summing up over everybody. But I'm getting a 1 if y is greater than 0. And so the sum of times where that happens is exactly how many people. That's my ny. So this little thing here is my ny greater than 0. And this thing up here, I just want to add up the x's where this happens. So another way to do that is I'm going to add up over everyone their x's, but I'm going to multiply the value of x times also this indicator function. Right? Because that way, if y is greater than 0, I get the value of x. It's just that x times 1. But if y is not bigger than 0, then this is going to be 0, and this just is not going to appear. That term is not going to appear in the sum. It's going to be a 0. It's canceled out. So this is a kind of more formal way of writing this, but I think this is kind of much more clear, right? You see immediately what it is that you're trying to do here, whereas this is not intuitive. What is well, you have to know what the indicator function is doing, and so this is kind of a case where notation that is a little less formal and a little more loosey-goosey, hand-wavy is actually clearer, easier to understand than notation that is more strictly defined. Whatever. Let's implement this in R. So this is the, again, I can use the same data. Let's get rid of this now. And let's implement this. So with the data, what do I want to do? I think the easiest way to do it is to subset to the people where y is greater than 0. And then take the mean of x. There we go. Again, you will see that number changes depending on what the data are. Okay. Just to show you, so this is kind of implementing the thing on the left. If you want to do it like the way on the right, just to show you that it's the same thing, we can say, okay, so let's compute the thing on the top. So that is the sum. Let's do it like this. So it's the sum of x times y greater than 0. So this is the numerator. And then the denominator is the sum of y greater than 0. You can see that's the same number if we had just done this. And in case it's not totally clear to you, what this is doing, the y greater than 0 data. So if I look at y, the column y, I get this vector, right? If I look at column y and I say, where is it greater than 0? I just get a vector of trues and falses. In this case, they're all true because y is by definition bigger than 0 everywhere. But these trues and falses you can interpret as ones and zeros. So when you do this multiplication, this is element y is multiplying each 1 or 0 times the element of x corresponding to it, and then adding up all those x's. So it's doing what we said up here. A little bit of just background, not entirely related to the course material. Okay, so next up, let's do the plugin for this probability. So this is the probability that x is greater than 0, given that y is greater than 0. So from like week 1 or 2 or whatever, when we are doing this, you know how to do this with the population data already, right? This is just the number of people where x is greater than 0 and also y is greater than 0, divided by the total number of people where just y is greater than 0 in the population. So all we need to do to get the plugin estimator is just compute this for the sample, right? So very simple. Again, if you want to be, this is informal notation, works perfectly well, very clear, immediate what you mean. But if you want to be very formal about this, right, you can also do this in terms of indicators. So like this, that works. And then again, these sums are across the whole data. Same thing. So this one, I'm not going to implement it in R because you already know how to do that. This is just a count. So you can either do it separately, like get the data set, first count this number, and then count that number and divide them. However you want to do that. We've already seen how to do it. This one, same thing, right? So let's just break it down. How would I compute that number? How would I compute that number? It's exactly what we already did up here. So the only difference is that this one you have to divide. This one, the numerator is different, and this is not a y greater, it's a y less than for this other version. So here it's this corresponds to this, right? And then you need to divide that whole thing by something that looks very similar. But now here we have less than. And then y less than, right? So this is and I'm going to leave the more formal one off, but this is the plugin estimator for this population quantity, given whatever data set that you get.